So the question of the day is, by the way, the day is 1600s. Is light a particle or a wave? Newton said he thought it was made of particles. Christian Huygens said he thought it was made of waves. They both had some ideas as to why, but neither of them could really back it up with experimental proof. But since Newton was more famous, people believed that light must be made of particles. Then Tommy Young comes along in the 1800s. And what Thomas Young did was, with his double slit experiment, prove that you can find the wavelength of light. And if light was behaving like a wave, and you could actually make it with this experiment calculate the wavelength of light. In the 1800s, by the end of the 1800s anyway, we were completely convinced light is a wave. And so, in fact, at this point, scientists started believing we've got it all. We know what everything is. We can use mechanics or energy conservation, momentum, electricity formulas, and now with waves, we could describe sound and light. There's pretty much not much left with physics to even explore. And that's the way it was in the end of the 1800s. But then a few little chinks in the armor started to appear. A few little problems that scientists could not explain start to pop up. One of those problems was what we call black box radiation. And a black box is a perfect emitter absorber of light. And basically what that means is if you shine light into this hole in a black box, it'll absorb all colors of light. And if you heat this black box, it should emit all different colors of light. Now, you don't really need to know much about black box radiation. Be more familiar with the phrase. It's usually given as a wrong answer, if anything, on the AP exam. Black box radiation, think putting a sword in a fire and making a graph of intensity versus a graph of intensity with the different colors or wavelengths of light. And there was this curve that came out of it that basically showed that there was certain colors where the intensity was the greatest and other colors weren't as bright. So when you put a sword in a fire and you heat it from red to orange to yellow, and it gets hotter and hotter and eventually white hot, certain colors were more intense than other colors. Again, you don't really need to know this because the math that goes along with this all involves nasty calculus. But the problem was that classical physics means anything earlier than like 1900 and when Einstein's about to appear here in the next slide. So classical physics had no way of explaining what was going on with this graph from the black body radiation experiment. Again, I know you don't understand much of that, and that's fine, but there was a problem with black box, I'm flying quotes here, black box radiation. Well, you know what, I was going to go on, but I'm going to introduce somebody's name here that you've heard in chemistry, Max Planck, or Planck. All right, I just double-checked to make sure there was a C in his name. Okay, Max Planck observed this stuff and what was going on, and he basically said, and again, I'm going to give you the end result of a lot of thinking that went on and a lot of ugly math that went on with him. But basically, he said something. I'm going to give you his equation, even though we're going to use a form of this equation in a little while. I'm not going to show you where it came from, mainly because I can't do the math anymore to prove where this comes from. But he said this here is a constant, not so strangely, if we now call it Planck's constant. He said basically this: the frequency of oscillations of the molecules of a substance when heated can only have certain values. 1, 2, 3. It's kind of, and in fact, you will see this explained, by the way, with harmonics an awful lot, where they relate these things to like the harmonics in a guitar string. So remember this black body radiation problem, and that certain colors are more intense than others. What Planck said is that when you put a sword in a fire, and let me tell you how this came about. They couldn't explain the graphs that they were getting with classical physics. So this man somehow came up with, he kind of fudged the math to figure out that if I only allow the frequency of oscillation, that's the atoms vibrating faster and faster when you put the sword in a fire, he said that if I only allow them to have certain values, what I come up with is that there's only certain energies that are the atoms of the sword can have when I place it in the fire. And this gets a word that we now use, which is huge in science. He quantized the energy. He said that there are only certain values that the energy could have. You've heard about this in chemistry because 35, 40 years later, Niels Bohr came along and he used this concept and he put his electrons only in certain orbits, all based on, this all comes from Planck. So Planck gives us the idea that there are only, quantized word here, that there are only certain values of energy that are allowed, that the atoms, it's not continuous like classical mechanics thought, but there are only certain values that are allowed for the atoms of a substance to have. So when you heat the atoms of a sword, they don't just randomly get more and more energy. There are only certain energy values that they're allowed to have. Think Bohr energy level diagrams of electrons. It's quite a bit like that. Here's the meat of what you need to know, something called the photoelectric effect. In the photoelectric effect, we shine light onto a piece of metal. That piece of metal has electrons in it that can be emitted. So those electrons fly away with a certain amount of kinetic energy. Where does the electron's energy come from? Well, there are two things that affect how much energy the electrons have. And those two things are the energy of the light minus the energy to ionize. There were no scientists in the late 1800s that had a problem with this concept. There was no problem with electrons getting emitted when you shine light onto a substance. They knew about valence electrons, not by a long shot, because this was within 10 or so years of J.J. Thomson, by the way, and the discovery of the electron. But they were okay with the fact that the electrons could be emitted from the metal. We have, again, I didn't really do anything with this when we did the charging of things back in January with fur and metal strips and rubbing a balloon on your head, and you transfer electrons from your head to the balloon, and then your hair all stands up. There's a device called an electroscope. And with an electroscope, what you have is a metal plate and then leaves down below that are connected together. And any charge that builds up on the metal plate will go down into these leaves. My board's off here. Will go down into the leaves, and then the leaves stand apart. These leaves are traditionally made out of gold foil, very thin, very easy for the electrons to build up, and they will shoot apart when the electroscope is charged. If, however, you come along and touch that electroscope with your finger, you'll ground it. That's your finger, by the way. All of the electrons will go onto your hand, and then the leads come back together. So an electroscope is a device that we can use to show that charge has been built up in a certain location. A balloon in your hair is a perfectly good device to do the same thing. So what scientists would do is charge up these electroscopes, shine light on them, and then as electrons left the metal, the leaves would come back together. Okay, wonderful. We're showing that electrons are being given off by the light. Scientists had no problems with the idea that this should happen. It's how it happens that was surprising, that scientists could not explain what went on using quote-unquote classical physics ideas. Einstein comes in. Einstein borrows from Max Planck and says, I think that the light can only have certain energy values, and those energy values he saw as little packets of energy. Oh my, Einstein sees light, like Newton did, as being made of particles, where each of these particles had a certain amount of energy, and he takes this from Max Planck, E equals hf. And based on how much energy each of those little bundles of light have, electrons may or may not get enough energy to become ionized. So Einstein said it's the frequency of the light that determines how much energy the packets have. And if the packets have enough energy, the electrons can be emitted. The important thing of this is that this is completely a particle view of how light behaves. And by the way, before I show you this little applet, and by the way, this is a repeatable experiment that you can repeat in high school labs now, and you can only describe what happens treating light as if it were a particle. Now, you can't treat light as if it's a particle and describe what goes on with the Young double slit experiment. To describe the Young double slit experiment, you got to treat light like it's a wave. I know this is annoying when you first hear it, because then your brain starts saying, well, which one is it? Ignore the wave part right now. We want to concentrate on the particle part. Treat light like it were made of particles. So this little demonstration is showing you first what's going on. We have an ammeter here. Why do we have an ammeter? It measures how many electrons are moving through a circuit. We have a battery here. The battery's to supply electrons to this circuit. Okay, where was I? Yes, Hal Fletch Starnes just came in for a half an hour visit. Okay, so we have this ammeter to measure how many electrons are being given off. We've got a battery that is cleverly used for this reason. Notice that what's going on here is that it's showing light striking the metal, and it's showing you photons. Oops, I used the word I hadn't described yet. Those little bundles of light energy, those little bundles of light that have energy, HF, where did I put you, my friend? This one right here. These little bundles of energy, HF, are actually called and I am so lazy, I'm going to just write it with the mouse. That is called a because it comes from the photoelectric effect, photon. Big word in physics, photon. That is a particle of light, not pihoton, photon is a particle of light. So this is already showing the particles, but I'm going to ask you to imagine if it was a wave again here in a second. And then it's coming off quick, but these little gray things going to the side are electrons being emitted by that metal. So those little electrons are coming flying off. If you attach the negative side of the battery to this metal plate, what that'll do is, here, let me turn the battery on. What that can actually do is slow down these electrons. So let me keep increasing the voltage. I'm making the battery get bigger and bigger. And, oh, here we go. Okay. So, well, unfortunately, they won't let me actually stop it. So here I have a current, reading the ammeter, a current greater than 200 nanoamps. It's the last time you used a nanoamp. And then 140. As I make the voltage of the battery bigger, I'm making the current given off here, the number of electrons, less and less. Oh, here, I guess I got it to become 0 at this point. So what I'm doing is setting up an electric field that's repelling these electrons. When I can actually stop all of the electrons, I know how much maximum energy those electrons must have. Using a battery, I can set up an electric field in this area, and that electric field can actually be used to stop the electrons. So it's stopped right now because I just put a pen and I got an ink layer going on. So I set up using the electric field here of the battery. I'm setting up an electric field here between the plates, and that sorry, my pen's off again. That electric field can be used to stop the electrons. These electrons all have kinetic energy. If I use that little formula, work done is Q delta V. The electric field, remember this formula? Got to know it for the AP. The electric field is related to the voltage. I'll even write volt there for you. So the charge of an electron times the potential difference, basically, of the battery gives you how much work the electric field can do to take away the charge's kinetic energy. So we've seen that formula before, written just like this. You can measure how much energy the electrons are emitted with using what we call the stopping potential. The stopping potential is what the voltage of the battery has to be to completely take away all of the electrons' kinetic energy. Okay, so, sorry, got a little technical there on you. You've got to know that. You're going to have to calculate stopping potential. So, and there's a beautiful little trick when I show you how to do that eventually here. So I got this light coming in and electrons being emitted. Let me change the color of light that's coming in. A green light. I use yellow light. Oh, notice this. This is what they noticed in the laboratory. The blue light, when it shines on the metal, gives off electrons with a lot of kinetic energy. See them zipping along? Green light gives off less, yellow light gives off even less, and red light didn't give off any energy whatsoever. Now, it depends on what type of metal you're using as to what color you actually don't emit electrons anymore. Now, this is the problem that scientists had in the 1800s. They thought of light completely as a wave. So if light were a wave, I'll see you in a second after I recalibrate. Welcome back. If light were a wave, what would it mean for light to have more energy? Light, energy. If light's a wave, energy is proportional to, whoop, I wrote wave again. If light were a wave, its energy, I meant to write it there, would be equivalent to its amplitude. Okay? If light were a wave, energy would be equivalent to an amplitude. So when I come over here in a second and I click these different buttons, if I increase the intensity or brightness of the light should come in with more energy. So if I'm doing this experiment, this is what they were thinking in the 1800s. When I do this experiment, if I use red light and I don't see electrons be emitted, clearly I should just use brighter red light. But when they did it, it still didn't give off electrons. So they used such high intensity red light that it melted the chocolate bunny rabbits they had in their pocket left over from Easter. I mean, we're talking intense bright red light, and it still didn't cause any electrons to be emitted. The wave theory crashes, no pun intended, apart here. If light were a wave, brighter light would mean more energy. But that is not what happened. Likewise, if light were a wave, the only difference between blue, green, yellow, and red, and ultraviolet and infrared, if you want to add those in, the only difference between these colors is simply the wavelength or frequency of the light wave. So that should have absolutely nothing to do with energy. Classical physics says the only thing that determines a wave's energy is its amplitude. So changing the color should have no effect on energy. But look, it does. Because in the experiment, they saw when I use blue light, electrons come off with more energy. When I use green light, electrons come off with less energy. When I use yellow light, look at this, they come off with even less energy. And red light, they don't come off at all. They don't have any energy because they don't come off at all. So this is where Einstein entered the picture and said, like this diagram animation is showing you, it's because light is made of photons, and a photon's energy, this was borrowed from Max Planck. Max Planck didn't know where this he mathematically came up with this formula, but he basically said, I don't know what the heck it means. He was so bothered by this formula because he just said basically, this is crazy. Here's my life's work. This is crazy. What's it mean? I don't know. So Planck hated this stuff. Einstein loved it. He was like, my God, don't you see, man? Light's not made of waves, Einstein said. Light's made of bundles called photons, where a red photon and a blue photon have different frequencies, so they have different energies. Now try to follow this. So the photons coming in, if I go way back, don't make me find it because I'll lose my ink layer. If we go way back to the beginning of the video, I was saying there were three important things. The energy the light comes in with, the energy the electrons, the metal requires to ionize the electrons, and then what's left over is the energy of the electrons themselves. So what Einstein said is, what you got to understand is the light's coming in with a bunch of different little bundles of energy called photons, and they have different energies based on their different frequencies. So when they come in, a blue photon strikes an electron with more energy always, multiple choice question, blue photons always have a higher frequency, always have more energy than red photons. So there's an electron sitting on this piece of metal here. And that electron requires a certain amount of energy. We ready for this? We call the energy the work function. There's a certain amount of energy. Some nice books call it W0. Your reference table calls it phi. The work function is the amount of energy required by the metal to ionize the electron. Think about it as the cost to release an electron. So here it is in a nutshell. The photons come in with energy based on their frequency. The metal requires a certain amount of energy before it'll release an electron. We call that the work function. The difference between those two is the amount of kinetic energy the electron zooms off with. So we write this, Ke, the energy of the electron, equals HF, oh come on, HF, the energy of the photon, minus the work function. That's the big equation for the photoelectric effect. The Ke of the emitted electrons is equal to HF, the energy of the incident photons, minus the work function of the metal. This equation could be used in an experiment, and it what's the word I'm looking for? Accurately measures how much kinetic energy the electrons have. Wait a second. Who's going to stand there and measure the speed 1/2 mv squared of an electron? Don't forget this. The way you actually experimentally measure the speed of electron is using that thing I call the stopping potential. And that's what this experiment's designed to do with the battery. You can determine how much kinetic energy the electrons have by doing Q times V. That's the charge of the electron times the voltage of the battery. And then the frequency of the photons is already known. By the way, didn't want you to talk about Thomas Young, but you know who told us what the frequency of all the different colors of light was? Thomas Young. Einstein doesn't say he's wrong. That's how we know frequencies, from Thomas Young, but don't think of the Young double slit right now. Okay, why? Because if you think of the Young double slit, when you fire photons at it, they should just go through like particles and not diffract like waves. So don't think about that, you silly person. So this is how you measure the kinetic energy of the electrons. And what we do is we call it Ke max, because different electrons actually require different amounts of energy to be released, because they might be at different places within the metal, closer to the surface, etc. So this is actually written as Ke max. The electrons emitted might actually have different kinetic energies. Don't worry, they'll never give you different kinetic energies. They always refer to just Ke max. So the formula relates kinetic energy to the energy of a photon and the work function of the metal. Based on those things, you can measure kinetic energy by doing Q times V, the stopping potential, and basically you got to go through and calculate. And sometimes you do this. You actually see it written as H instead of F, it's C over lambda, because the speed of light in a vacuum divided by wavelength. So you might see it written like that as well. They might tell you, oops, you don't see that. They might say to you, the wavelength of the incident light is, and in that case you use the equation with lambda in it. Or they might say the frequency of the incident light is, and then come over here and use the original equation I wrote with frequency in it. Okay, now remember how when I shined different colors of light on, when I got to red, red did not cause the emission of electrons. There's the minimum frequency, and this is called threshold frequency. The minimum frequency that causes the emission of electrons is a special frequency called the threshold frequency, and we label it with an F naught. That is the frequency of the incident photon that actually the smallest energy that can cause the emission of an electron. You understand that? If blue photons have more energy, let me kind of do it with sizes of ease. Blue photons have a certain amount of energy. Green photons have less energy, so they have a less amount. Yellow photons, I don't have a yellow pen, Yellow photons have even less energy, and my smartboard's off again, gosh darn it. Red photons have even less energy, and I can't really draw E's because my pens are way off. So the energy of the incident photons depend on the color. The bigger the frequency, the more energy the photons have. There's a smallest frequency, in this case it would be yellow, that can still cause the emission of electrons. We call the frequency of the smallest color, the smallest frequency that causes electrons to get emitted, we call that the threshold frequency. When you find that frequency, that's when the frequency of the photon matches the work function, and the kinetic energy of the emitted electrons will actually be at that point 0. When the incident photons have the threshold frequency, the kinetic energy will be emitted, the electrons will be emitted, with 0 kinetic energy. In other words, the work function is equal to h times the threshold frequency. Okay? Big formula, and then these two are the same thing. The really big formula. Just as a little, kind of like this. Delta U is Q plus W, but you can find W other ways. And you can find Q other ways. And you can find delta U other ways. So the formula, the big formula for this one, for thermodynamics, was the first law. The big formula for the photoelectric effect is that the kinetic energy of electrons is equal to the energy the photons came in with minus the work function of the metal. But there's another formula to find work function, and there's another formula to find the kinetic energy of the electrons. But that ties it all together. This is strange stuff. When Einstein wrote this paper, this is one of 5 seminal papers he wrote in 1905. When he wrote these papers, scientists thought he was completely nuts. People did not quickly say, "Oh yeah, Einstein's onto something here." It took a while for people to start buying into this stuff. And this was not as bad as one of those other papers on special relativity, which took even longer for people to buy into. Just got a text. Dick Clark has rocked his last New Year's Eve. Farewell, Dick Clark. Okay, so photoelectric effect. Let me just kind of go through this again. Red's not emitting electrons. Wave people said, well, then just make it brighter. Brighter means more energy. Still didn't do anything. Einstein said that's because red photons don't have enough energy based on their frequency. Yellow light would emit some electrons, but red none. And wave people are like, we have no idea what's going on. We don't know. We can't explain that at all. But of course, red people said, if I increase the intensity of the yellow light, I should get them coming off with more energy. Notice that doesn't happen. Yellow, if I have low intensity yellow light, notice the general speed here. It's showing the electrons coming off. If I have brighter yellow light, I get more electrons coming off, but they come off with the same kinetic energy. Really bright yellow light, I get even more electrons coming off, but with the same relative kinetic energy. Do you understand what Einstein thought was going on with brightness? The brighter it is, the more photons there are. The more photons that come in, the more electrons get struck, the more electrons are emitted. So Einstein was able to explain to the scientists why brighter light caused more electrons to be emitted. Not with more energy like the wave people thought. Did you see me waving my finger there? Not with more energy like the wave people thought, but simply more of them at the same energy. All right, we're approaching 30 minutes here, and you don't like that, so I better stop. This photoelectric effect is one of 3 main topics on modern physics that we learn, and modern physics is approximately 17% of your AP exam. Do the math. 6% of the questions are going to be on photoelectric effect. This is pretty big. You got to know it. You might want to read a section in the book on photoelectric effect if you're not quite following all the stuff I said. And I don't expect you to grasp it all immediately. But guess what? We don't have a lot of time to spend on it. We're approaching the end of the year. You needed too much time on your horizontally fired projectiles now, didn't you? Photoelectric effect. Read up on it.